Hello everybody, welcome back. Today we are going to talk about something that is surely very different from anything you've seen before, I bet, and that is called conformation of alkanes. All right, so what we mean by conformations of alkanes is it's sort of a description, a model of how we can have movement within a molecule, right? You know, if you think of a molecule, and when we think of a molecule, let's specifically in this case think of an alkane, propane, butane, whatever. The molecule is not just sitting there static in space, right? You of course know from other chemistry classes is that molecules are always moving around. They're bouncing around off different walls of their containers or each other or whatever. However, one thing that we don't necessarily think about is movement within the molecule. All right, and that's something that we can see. All right, if we draw a molecule that's got a single bond, all right, let's just say here we have a carbon-carbon single bond. Let's say it is just ethane, CH3CH3. Okay? You can think of this bond between the two carbons much like an axis, right? You can get rotation, free rotation around that axis in 3 dimensions. A very good analogy is thinking of a helicopter blade, right? You have a helicopter blade. That's sort of like a carbon here with the three three hydrogens on it. This can spin, literally spin around the centralized axis, sort of like the axis or the axle that the rotors are attached to in a helicopter, right? So constant spinning around single bonds, right? We have what's called free rotation, right? And what's interesting is as you get free rotation around single bonds, you can get different orientations in 3 dimensions of the different atoms with each other as well as electrons with each other. All right? So by drawing different conformations, we can kind of see how the relative positioning changes and also how that affects the stability of the molecule. All right? I want to lead off by saying or recommending that if you really want to have a good hands-on way of exploring this, I would heavily recommend that you invest in a molecular model kit for organic chemistry. I will try and remember to post a link to a good one on Moodle so you guys can take a look. They cost anywhere from about probably $15 to $35, depending on the ones that you get. And it's not required by any means, but I think it's a very good investment. I would recommend that you get one. If you get one, I will let you use it on quizzes, tests, anything like that, because learning how to use those models is an important skill. For those of you who don't want to put out the money for a molecular model kit, but still want something to work with, you can actually make your own by using toothpicks and colored marshmallows or colored gumdrops. And again, if you want to bring those in for a test, or use those on a test, that'll work too. Plus, you'll have a snack, which is kind of cool. But either way, I think having this hands-on tool can be really helpful in understanding this. Today, what I'm going to do is I'm going to show you how this works, though. I'm going to show you how we can model it, how we can draw it on a piece of paper. And also, we're going to look at some 3-dimensional animations that show these movements. So, should be fun. All right. So let's start off with ethane. Ethane's a good model. All right. One thing that I think you'll notice is if we look at an animation of ethane that's done by a ball and stick, and you see the 3-dimensional arrangement, you can see that there's a couple of different ways that we can have them arranged. All right. So let me pull this up. I have this already queued up. This is on a website called chemtube3d.com. It's got lots of good 3-dimensional representations of various things in chemistry. This one right here, and I'm just using my finger to move this around, so this works on tablets, smartphones, or laptops. This is a model of ethane, and if you look at it, you can see the CH3 groups are oriented in a very specific way, right? If you look at the green atom and you look at the blue atom, you'll notice that they're lined up sort of opposite to each other, right, when you look at it at an angle. However, we could very easily spin around that axis to get a different conformation. Let's see. Yeah. Right, here's a different representation, right? So you see those atoms are oriented in a different state. You get constant 360 degrees rotation, right? So the positions, the relative positions of these atoms to each other is constantly changing, right? So with these, it's useful to be able to draw structures that can represent these different conformations. And that's where drawing Newman projections comes in. All right, come on, eraser. There we go. All right, Newman projection formulas. Specifically is sort of a way of drawing the molecule, highlighting a specific single bond, and showing how orientations change due to free rotation. All right, so let's start off with ethane. CH3, CH3. All right. Now, there's guidelines I'm going to give you for drawing Newman projections. There's slightly different ways you can go about it, but this is going to be the way that's easiest, I think, and give you a little bit more structure in learning the process. All right, the first thing is you want to identify a bond that you want to sort of look down the barrel of, right? If we go back to this, you know, I got this carbon-carbon single bond here that I'm just sort of looking at straight on, just like that. All right. I'm going to represent those two carbons as, come on, there we go, a dot and a circle. The dot represents the front carbon. The circle represents the back carbon. Okay? And there's sort of an imaginary bond in between. Now, you know the front carbon also has 3 bonds coming out from it, in addition to that carbon-carbon single bond. The back carbon also has 3 bonds. All right, so that's how we represent them, like that. You don't necessarily have to draw them exactly like this at the beginning, but this is the way I always like to start. I always like to start drawing them sort of spaced apart from each other in this manner. And I always like to, it's just a personal preference, I like to make the front carbon have one going straight up and the back carbon having one going straight down. Again, you don't actually have to do it that way, but I think it makes it easier. All right? And then the last thing that you draw is you draw the other atoms or groups of atoms that are attached to the bonds, right? So let's just say this one's the front carbon and this one's the back carbon, right? If we look at the front carbon, what's attached to it? Well, we have 3 hydrogens, right? So I'm going to draw those 3 hydrogens. We look at the back carbon. Well, it's also got 3 hydrogens. Like I said, this is a simple example. So let's draw those in. Okay? And there we go. There is one of our Newman projection formulas for ethane. All right, you notice how all the bonds are kind of offset from each other, right? None of them are perfectly lined, none of them are lined up with each other. In fact, they're kind of staggered, right? Guess what? We call this the staggered conformation. Pretty creative, huh? I know. Yeah, staggered conformation. In the staggered conformation, the bonds are offset. They're not lined up with each other. All right? Now, it's not going to stay in this position, right? Like I said, we get constant rotation. When you want to draw another Newman projection formula, what you do is, again, the iPad doesn't like it when I hold the stylus down for a second. Draw the same circle and dot, all right? Now, what you have to do is show what's going to happen when you rotate around that single bond 60 degrees, all right? The easiest way to do this is to pick one of the carbons, doesn't matter which one, back or front, keep it stationary, and then spin the other one like a propeller, right? My personal preference is to always leave the back carbon the same and to spin the front carbon. You could choose to do it the opposite way. Just make sure that every time you spin it, you're spinning the same carbon, all right, around the same carbon, all right? So I'm going to show what happens if I spin the bonds on that front carbon 60 degrees. Now, you're actually going to end up in a situation where the bonds are lined up with each other. You have to sort of think three-dimensionally here, because I have to offset them a little bit so you can see what's going on. But this is representing an example where the bonds are directly lined up. All right? And then you go ahead and draw what's attached. Okay? When they're all lined up like this, this is called an eclipsed conformation. And that's a pretty good descriptive name, right? It's sort of like an eclipse when the moon goes in front of the sun, or vice versa. All right. If we look at our animation here, let's see. I'm going to pick this. You can see that again, you go constantly in and out of staggered, eclipsed, staggered, eclipsed. All right, and you can see that here. I'll start the movie again so you can see it. Right now it's in the staggered state. Staggered, eclipse, staggered, eclipse, staggered, eclipse, staggered. And that's going, then it goes backwards. All right. You might notice here, as we're spinning the molecule, we have this graph, right? On the y-axis here, this is energy. All right. So basically, as you go up the y-axis, you're increasing the energy of the molecule. All right. The x-axis is just simply the changing angle. All right. So every time you go 60 degrees, it goes over to the right. Okay. You'll notice here that as I'm going to try my best to pause this at the right times. Whenever we're in a staggered state, the energy level tends to be low. I didn't get it at the top, but close enough. All right, but when we go into an eclipse state, we have a much higher energy. Eclipsed, I messed that up. Let me try it again. Staggered, low energy. Eclipsed, high energy. High, low, blah, 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 blah. Okay? All right. Crud. Ran out of screen. There we go. So why the energy difference? Well, whenever we talk in chemistry, when we talk about high energy and low energy, that can be related to stability of a system, right? Whenever something is more stable, it's going to have a lower energy. So the staggered is definitely the more stable out of these, right? High energy species are not as stable. That means the eclipsed is not as stable. Why is this? Well, I'm going to erase some of this to try to get some of the junk out of the way. Give us a little bit more room to work. It all has to do with the relative positioning of the electrons in the bonds. All right? Let's just compare two bonds here in each diagram. Let's compare this bond on the front carbon with this bond on the back carbon. All right? You see how they're kind of far apart. They're not exactly very close to each other. They kind of exist in their own little areas. Whereas if you look at these two right over here, they're lined up perfectly in front of each other. This means these two electron pairs, right, in each of those bonds, they're closer to each other on the right structure, the eclipse structure, whereas they're further apart here. Electrons are negative. What happens when like charges get close to each other? they repel, right? That is not an energetically favorable situation. So whenever you get these electron pairs close to each other like this, they don't want to do that. They want to resist each other, right? So it takes energy to get them to go into that arrangement, okay? This extra energy that's introduced because of eclipses is called torsional strain, all right? So eclipsed conformations are less stable than staggered conformations because of added torsional strain. All right. So that's a pretty simplistic example because, hey, we only have 2 different conformations. But guess what? We can have more. Okay? In fact, we can get, in most molecules, unique arrangements by going around in a full circle in 60-degree increments. All right? Let's take a look at butane. All right? If you remember, butane has 4 carbons. So what we're going to do is we're going to be looking at what happens when we rotate around that carbon-carbon single bond. All right? This one's going to be a bit more complex. All right, so let's start off. Come on. Come on. Good enough. All right, so draw our circle and our dot. Let's just say, that this is the back carbon, this is the front carbon. Doesn't really matter which one's which. All right, so I'm going to draw my bonds here in the back and in the front. I'll start off with a staggered. Okay, so let's look to see what else is bonded to these carbons. To the back carbon, you have a CH3 group that's hanging off, right? So I'm going to represent that. And also, not drawn, you have your 2 hydrogens. Okay. If we look at the front carbon, well, again, we got a CH3 group, and we have 2 hydrogens. All right. I want to, again, represent the fact here that where you put these initially is entirely arbitrary. Like, I could have put, the front CH3 group, like, over here, but I just didn't want to. But I could have, all right? Because eventually you will get all these positionings as you rotate through. All right? So, hey, guess what? We've got a staggered conformation here. All right? We rotate at 60 degrees. I'm going to leave the back carbon alone, everything the same. All right? So now, when we rotate 60 degrees, we're going to go into an eclipse. All right? So if we keep track of things, the CH3 that was pointed directly up here in the front is now going to be eclipsing that H. Having stylus issues. All right, you're going to have an H eclipsing that CH3 and an H over there. Okay? So we have an eclipsed. Rotated another 60 degrees. It does that every time I hold the stylus down, which sucks. So, let's see. I'll make my dot by doing a little bit at a time. Kind of a messy dot, but hey, it works. All right, so that's the same. Blah, blah, blah. All right, now we're going to go into another staggered conformation. You just keep going round the merry-go-round. All right. So we got a staggered. Now you'll notice one thing here, though. The 2 staggers don't look exactly the same. Right? If we focus on the largest groups on each carbon, right, that's going to be the 2 methyl groups. In the first structure, these 2 are diametrically opposed to each other. They're as far apart as they can possibly be. Whereas over here, They're still staggered, but they're definitely closer to each other than they were. There's actually special terminology that we use. All right? The one on the left would be called staggered, comma, anti. That means your two biggest groups are anti to each other, completely diametrically opposed. Whereas this one would be referred to as staggered gauche, Gauche. Still staggered, but closer in proximity than anti. Okay? I would love to be able to draw all the Newman projections for butane on one screen. Unfortunately, I'm out of room. So, do this. You have the ability to rewind, so you can kind of go back and forth. I'm going to label these. I'm just going to label this one 1, 2, 3. All right, and you can kind of associate those with the numbers. All right. Alrighty. Well, let's keep on trucking. We got more structures we can go through. All right. So our last one was a staggered gauche. All right. As you might guess, we're now going to rotate back into an eclipsed. By the way, when you offset these eclipses, it doesn't matter whether you offset it to the right or left. It's fine. It means the same thing. All right. Now, again, you'll notice here, this eclipse doesn't look exactly the same as the last one, right? In the last eclipse, we had a CH3 on one, side on the front, and an H in the back. And we did that a couple of times, right? In this case, we actually have the two CH3s directly eclipsing each other. So, do we have another name for this? No, we don't. Why not? I have no idea. I think we should. I don't know why we can't, use anti and gauche for eclipses, but we don't. Again, you can contact the International Union of Pure and Applied Chemistry because they come up with the rules for this. But it is important to realize because later on we're going to be looking at relative stabilities. All right. Okay, we're going to rotate again. Keep on going. We're going to go back into another staggered. And you'll notice here, as we sort of keep passing through, we're going to go through another staggered gauche. And then do it again. And we'll go through one final eclipse. Now, obviously, the molecule would keep spinning indefinitely, but you'll notice if we do this again, we just end up at the original staggered anti. So these are the 6 Newman projection formulas for butane. And I'll label them 4, 5, and 6. Okay? Now, this introduces a new layer of instability that we can have, besides just torsional strain, right? You still have torsional strain every time you have an eclipse, but now we have to worry about something else. We have to worry about something called steric strain. And you're going to hear this phrase a lot in different contexts. We talk about this quite a bit in organic chemistry. Basically, when you hear steric strain, that means instability due to crowding, right? Think of an elevator. You get on an elevator by yourself, you feel fine. You can, breathe easy, you can spread out, you're good. Otherwise, though, let's say you get on an elevator with 7 other people, then you're a little crowded. You're probably a little uncomfortable. You're not feeling as good as you did before, right? This is introducing instability, it's introducing extra energy, right? This happens between larger groups. So specifically what we're going to be looking at really is going to be the CH3 groups, right? For example, if we were to compare, and I'm going to erase some of this here just so you can see. If we were to compare a staggered gauche with a staggered anti. So I'm going to just draw this little fella back up here. Okay, let's look at the CH3 groups. Here, CH3 definitely is the largest group, right? It takes up a lot more room than the H's. In this case, the largest groups are diametrically opposed. They're as far apart as they can get. Whereas over here in the gauche, they're a little closer to each other, which means they're probably going to have a bit more crowding. And that creates a little bit of instability. All right, so staggered anti-conformations are more stable, lower energy than staggered gauche. Now, they're both better than eclipsed, right? Torsional strain is a larger factor than steric strain, right? So all staggereds are going to be better or less energetic than all eclipses. But within staggered, you can have different conformations that have different amounts of crowding. And it's not just within the staggered ones either. Even though we don't have special names for them, we have differences that we can observe in the eclipses. Let me, again, draw a couple of sample structures. All right, in this example, the CH3s are not, whoops, that's supposed to be an H, sorry. In this case, the CH3s are not directly eclipsing each other, but in the second, oh, that's terrible. Got my dot way off center. How embarrassing. All right, that'll do. So in this case, though, will do. Okay. I'm talking to myself now, but pardon me. In this example, the CH3s are eclipsing each other. You have two large groups that are directly in front of each other. This situation is worse off as energetically, it's higher energy than this situation, right? Because you don't have on the left the two biggest groups directly eclipsing each other, right? So in this case, the structure or the drawing on the right would have a higher energy than the one on the left. Let's show you. Let's take a look at this. I'm going to go backwards, and I should be able to get to butane. There we go. All right. So here's butane. You can see we can play it around with our fingers as well, and you can click on different conformations. And just like we did with ethane, we can look at the energy profile moving. And you see this one's not as simplistic as the last one. All right. So if you look here, they're starting off with butane in a staggered anti, and that's at a very, very low energy. Whoops. This is not the interactive one. Let me move on. I want the interactive one. Darn it. Whoa, okay. Okay. So here, staggered anti, very low energy. Now, I rotate that. This is supposed to be interactive, damn it. It's not being very interactive. Maybe that's not optimized for a tablet. Oh well. How about just playing the video? That would be awesome. I've never done this on a tablet before. I've always done it on a laptop, so technical issues. Alright, but anywho, I don't know what just happened. Oh, yay. I accidentally figured it out. Yay me. Here we go. So you can see as we're spinning through the different conformations of butane, it went through different energy cycles. All right? And again, this is really tricky. I have to pause it in just the right place. So we have a staggered anti. All right, close enough. This is going to be our first eclipsed conformation, but not the eclipsed conformation that had both CH3s in front of each other. Right? So as you might expect, this is higher in energy, but it's not the highest energy conformation we have. All right, then we rotate into a staggered gauche, right? And you can see staggered gauche, definitely lower in energy than the eclipses, but definitely higher than the staggered anti. All right, I was a little off on pausing this one, but you get the idea. Let me see if I can run it back. There we go. Oh, nice. All right, in this case, now we're at another eclipse, but in this case, the methyl groups are directly in front of each other, right? So you're maxing out on steric energy, steric strain, in addition to your torsional strain. So that's at an energy maximum. Back to staggered gauche, and in this particular case, the staggered gauches are the same, and it finishes. So definitely, as you get more complex, you can have more complex states of existence. All right? And like I said, it can get, even more fuzzy sometimes. Hypothetically, I'm not going to go through all these, but let's say hypothetically, you had something like this. I'm trying to think of a good example. Give me a second. Wow, I really wish I'd picked an example for it. I'm blanking. Blah, 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 blah. Let's see. Let's say you had something like this. This is definitely a little bit more complex. All right? And let's say we were specifically looking at the Newman projections around that bond. Okay? I'll get you started. All right, so front and back carbon. Let's just say this is back, this is front. All right, so on the back carbon, we have a few different things. We've got one H on that back carbon. We also have a methyl group, CH3, and we also have an ethyl group, CH2. CH3. And that's right here, here, and then the H that we didn't draw for skeletal structure. All right, on the front carbon, we have an ethyl group, and we have two H's, okay? So there's kind of an opening Newman projection. See if you can draw the rest of the Newman projections for this structure. Now I think you'll find out this one's definitely a bit more complex. For example, I think you're going to have more than one situation where an alkyl group eclipses another alkyl, right? What do you think would be less stable? An ethyl eclipsing a methyl, or an ethyl eclipsing another ethyl? Take this, try to draw all the Newman projections, and try to sketch out your own little energy profile to see if you can plot the relative energies to each other. All right? If you have any questions about this, or want me to check your answer or anything, please let me know. I'd be happy to do so. Until next time, keep practicing, and I will be back with probably one more video. All right? Thank you. Bye-bye.